Hello everybody. So in this lecture we're going to talk about how do you choose the statistical tests when x is continuous. So in the last lecture we discussed how do you choose tests and which tests you use in different situations when x was categorical. Okay, sometimes x is a continuous variable and we need to know which methods are valid whenever x is continuous. So if x is continuous, you're typically looking at how the outcome or response, so your y variable, changes as the value of x changes continuously. Okay? And although not all, most testing problems involve either a categorical x, which we talked about last time, or a continuous x. Okay? So as I said, if x is continuous, you're looking for how the outcome or response variable y changes as the values of x change continuously. So you're essentially, most of the time, it's like trying to identify some type of trend. Okay, if the outcome is also continuous, then usually you're interested in how the mean response changes as the values of your x change continuously. If your outcome variable y is categorical, let's just say it's a yes or no for describing whether or not the event happened, then typically you're interested in how the probability of this event changes as the values of x change continuously. Okay, so let's look at a couple different clinical scenarios and the appropriate tests or analyses that you could do in those specific cases. So we're here. So one clinical example, you could be asking, is there a linear relationship between cholesterol, either HDL or LDL, and age in adults? Okay. So let's think about this type of question. So the cholesterol level would be a continuous measure, and age is essentially a continuous measure as well. Even though we measure it in years, if you really want to nail it down, time can be thought of as a continuous. So for this type of analysis, we have a continuous x and a continuous y. So a correlation analysis would be appropriate. So you want to know if there is a linear relationship between a continuous variable x and a continuous variable y. So you would typically use this Pearson correlation coefficient to assess that linear relationship. Okay, you could also ask a question. So we're in this part. Do age, height, or weight predict systolic blood pressure? Okay, so again, you're interested in the association between a continuous response, systolic blood pressure, and age, height, or weight. So in this particular situation, the keyword is predict. So you want to know how these variables, age, height, or weight, predict systolic blood pressure. So for this kind of question, we would typically be interested in a linear regression, and the slope, which is a parameter that we're going to estimate in a linear regression, tells us how changes in one variable affect the other variable. Okay, so the actual research question here is, does the mean response increase or decrease linearly as x increases? Alright, and finally, we could have a clinical question like this. Is there a relationship between cholesterol and the probability of being hypertensive? Okay, so if our y value was hypertensive or not, so hypertensive versus not, then we may be interested in predicting the probability of an individual being hypertensive given their continuous cholesterol levels. So our y value is an event, so it's dichotomous or categorical, and our predictor variable would be cholesterol level. Okay, so in this situation we could use what's called a logistic regression, and we're going to talk some about that. And a logistic regression also gives us a way to an easy formula to compute an odds ratio from the output that we get from a logistic regression. All right. So the first thing is this correlation that we're going to discuss. So correlation is essentially a measure of the strength and direction of a linear relationship between two. So correlation is a measure of the strength and direction of a linear relationship between two continuous variables x and y. And the formula for the sample correlation, you don't have to remember it, but if you'll consult your book, you'll see that it looks something like this. So we've got a summation in the top, in the numerator, and this summation looks like the sum of the cross products between the deviances of x and its mean from its mean and the y's from its mean, divided by some notion of the variation in each one of x's and y's. So we have underneath this square roots, summation xi minus x bar squared, summation yi minus y bar squared. Okay, and what this sample correlation tells us is how x and y covary together, and then in the bottom what we have is some kind of scaling which puts this r in between -1 and +1. Okay, so a correlation is some number between -1 and 1, and if it's 0, that indicates no linear relationship between x and y, and a correlation greater than 0 indicates a positive linear relationship. One that is less than 0 indicates a negative linear relationship. If any of these guys are identically equal to 1, that's a perfect relationship. And the closer that the correlation is to -1 or 1, the stronger the relationship. So one important point to keep in mind, though, is that correlation does not imply causation. Okay? So here are some different plots of data points under different correlation settings. This first one here is essentially looks like a random scatter of buckshot. So R is 0 here. There's no linear relationship between your x value and your y value, and it just looks like random scatter. In the top, what you'll see is starting from 0.5 and going all the way to 1, positive correlations, and in the bottom row you'll see starting from -0.5 all the way to -1, negative correlations, both in increasing magnitude, so as you go from left to right. Okay, in the top you'll see that in this very first graph here, even a correlation of 0.05 almost still looks, I mean, there's some type of trend that you may see here, but still things are kind of spread out. Now immediately once you get to 0.9, you see that the points get tighter and tighter on the line. At 0.99, it's virtually, points are falling on the straight line, and then as if the correlation were 1, these points would fall exactly on a straight line, indicating a perfect linear relationship. Okay, same thing's happening for the bottom row here, except that we have negative correlation. So -0.5, you still see the general kind of behavior as 0.5, except the direction has changed a little bit, but you still have a lot of scatter. As you increase the correlation to an absolute value or in magnitude towards this 1, you see things again are getting tighter and tighter on the line, on these lines, except in a negative direction. So the slope is negative. Okay. So let's look at an example of this correlation, and we need to keep in mind that these correlations that we're doing here are for this so-called Pearson. So I'll write Pearson correlation coefficient. So there are non-parametric alternatives to this Pearson correlation coefficient, and they essentially rely on the ranks of the data. So it looks like a Pearson correlation, but after the data has been ranked. Okay. So for this example, we've got 20 subjects with hypertension, and they're measured on mean arterial blood pressure, age in years, weight in kilograms, body surface area, so we're going to abbreviate that later as BSA, duration of hypertension, so how long they've been hypertensive, basal pulse, and some measure of stress. The question here is mean arterial blood pressure correlated with these 6 variables? Okay? This is what the output from the corresponding correlation analysis for this data set looks like. Alright, so what we have here are our different variables: our age, weight, body surface area, duration, pulse, basal pulse, and measure of stress. And what we have underneath this are the computed sample correlation. So these are the sample estimates of the true underlying correlation coefficient between these different variables and arterial blood pressure. Okay, so this is the sample. These are the sample estimates of the correlation from that computed using the formula that I showed you earlier. And these are the corresponding p-values for this test. H naught rho equals 0 versus the alternative that rho is not equal to 0. So rho here, again, you'll notice this is a Greek letter, is the true population. So true population correlation. Okay, and these R's that you see here are the estimated, those estimates that we estimate from the data. Okay, so if you, for instance, wanted to estimate the true population correlation between, let's say, age and arterial blood pressure, you would take this guy. This would be your sample estimate of that quantity. Alright, and what you see based on these p-values is it looks like age is significantly associated with arterial blood pressure. Weight is, body surface area. Duration of hypertension is not, because our p-value for that test is not less than our 0.05 significance level. This one is less than 0.05, so basal pulse is significant, but measure of stress is not significant because the p-value for that test is not less than our significance level of 0.05. Alright? Okay, so that's all there is to really to this correlation, bivariate correlation analysis. You get a sample estimate, so let's take this away. You get your sample estimates, you get a p-value. You can also construct a 95%, approximate 95% confidence interval for R. It's usually based on the Fisher Z transform. So a Fisher Z transform for confidence interval. And the mechanism for doing the hypothesis test and making decisions is virtually identical to the things we've done before, except we're making a decision for a different parameter, in this case correlation. Alright? We can also look at these kinds of models where you have a continuous predictor and you have a continuous outcome in terms of simple linear regression, and in the future we'll look at multiple linear regression where we have more than one X variable. But to start it out, simple linear regression, it's actually related to correlation, and it's useful when you want to predict a continuous response, say Y, with a single X variable, both continuous. Okay? It turns out, though, that the X variable doesn't necessarily have to be continuous if you want to look and do a regression analysis. It can also be categorical or discrete. You just enter in some dummy variables into the model. But right now we're going to look at simple linear regression where x is continuous and y is continuous. Okay. So multiple linear regression, it would just mean that we had more than one predictor variable. Okay. More on this later. But if we're in a simple linear regression situation, what we have is our response variable is equal to some linear function. So we have a intercept. We have some parameter which is a slope times the value of our predictor variable plus some residual, random residual. And typically the assumption that's made on this residual is that it's, so we'll say epsilon is typically assumed to be normal with some mean and variance. Now, of course, assumptions need to be checked, and if you wanted to carry out inference, say, based on the t-test, you would need to check for normality of the residuals. But this is the typical modeling assumption for a linear regression. Okay, and what happens is once we see the data, we try to find the best line going through these data points. So what we'll have if we're doing a regression analysis and if we're doing a correlation analysis is we'll have data on x and y for each individual, and if we were to plot that, it would look something like this, and a linear regression would try to find which line fits through this cloud of points the best. Alright. So in order to do that, essentially what we have to find is the beta hat and beta naught hat and beta 1 hat that make this line fit through these points as best as possible. Alright, once we have those, those estimates, specifically this one, we can carry out a test for whether or not beta 1 is equal to 0, so that would be a null, versus an alternative that it's not equal to 0. Okay, so if we were to say reject h0 for a linear regression, then we would be saying that x and y are linearly related. Okay. So we would be testing whether the slope is 0 or not. That would be this test. Alright, and as I've said on the previous slide, if we make a normality assumption on the residuals, so if this assumption does indeed hold, then we can test this slope equal to 0 based on the t-test. Alright, so if beta were equal to 0, then that would indicate there is no linear relationship between our x and y. If beta was greater than 0, it would indicate a positive linear relationship. And if beta were less than 0, if our slope beta 1 were less than 0, it would indicate a negative linear relationship between x and y. Okay? And at the end of the day, we should wind up getting the same p-value if we look at this problem as a regression problem or whether we look at it as a correlation problem. Okay, so for correlation, you're going to get the same R regardless of whether you switch x and y. So regardless of which variable you call x and which one you call y. For regression, you're going to get a different slope. The test is going to be the same, but you're going to get a different slope because you're using one variable to predict the other one. Okay, I'll mention it again. Neither one of these are going to imply causation. Alright, so let's go back to this arterial blood pressure data, and let's ask if body surface area or weight are individual predictors of this arterial blood pressure, mean arterial blood pressure actually. So what we have here is a scatter plot of this data, and each of these points is going to be the weight in kilograms for observation I, so xi and yi, which would be arterial blood pressure. Okay, so xi would be weight for observation I, weight for obs I, and this y would be arterial blood pressure. So I'll abbreviate arterial blood pressure for OBS, observation I. Okay, and what this green line is the fitted line. So it's the line that we get from doing this least squares estimation that I've mentioned on the previous slide in order to find beta naught hat and beta 1 hat. So this line is essentially the best line that we can find that fits through this cloud of data points, or this set of data points. Alright, and if we carry out this analysis with a regression, then these are the results that we get for this set of data. We wound up with an estimated slope of 1.2, so our beta 1 hat was equal to 1.2, and a corresponding 95% confidence interval looks like this. So from 1.0 to 1.4. Alright, the p-value that we get from this is again significant. It's small. It's less than our significance level of 0.05, and this is in agreement with what the confidence interval tells us as well, right? You don't see 0. Is 0 in this confidence interval? No. Okay, so the analysis or the decision based on the confidence interval is in agreement with what the decision would be based on the p-value. We would reject H naught. So what would H naught here be? Recall, it would be that beta 1 is 0. So we would be rejecting this. So our conclusion would be that there is a linear relationship between weight in kilograms and arterial blood pressure. Alright? So let's take some of this away. So what that would mean is, let's just say we increase weight by 5 kilograms. Well, that would lead to a mean increase of 6 millimeters of mercury in arterial blood pressure. How did I get that? How did I come up with that? Well, I just multiplied this slope by an increase of 5 kilograms. So 1.2 times 5. And that would give 6 millimeters of mercury increase in arterial blood pressure. Okay, so for every unit that we go over on the x-axis here, what this slope tells us is that we should expect an increase in the mean arterial blood pressure. So this height would be 1.2. Alright, we can also look at another one of these other measures for this data set, which is body surface area, which I've abbreviated as BSA. And this is a scatter plot of the points. So xi, yi. The yi is still the same here. It's the arterial, so arterial BP for obs I, observation I. But now x is the body surface area for observation I. So BSA for obs I. So that's this cloud of points that you see here. All these points are those XY pairs. And what this green line is, it's the line that fits through that cloud of points the best. Okay, so after we do our regression analysis here, where we now have body surface area as a predictor of arterial blood pressure, our slope wound up being 34.4, so our beta hat estimate from this least squares line fitting wound up being 34.4, and the corresponding 95% confidence interval is from 24.6 to 44.3. So again, you see that the null value, so 0, is not in here. So our null value, beta 1 equals 0, is not contained in this confidence interval. So we would reject H naught, and that is in agreement with the p-value that we get from this test. So P is less than 0.0001, which is less than our significance level of 0.05. So we would reject H naught. And the interpretation is similar to the interpretation on the previous slide. Alright. Okay, so we've talked about continuous x and continuous y. Well, how do we handle continuous x but discrete y? So, that's going to lead us to this topic of logistic regression. So it's similar to linear regression, except that you should use logistic regression when y is binary. You should not use linear regression when y is binary, because what will happen is you'll get values, predicted values, that are outside the range of possibility for your y. So a linear equation can give you any number between negative infinity and infinity, but y can only take values 0 and 1. So it's not appropriate to use linear regression when your response variable y is a 0 or a 1. So the assumptions of linear regression don't make sense here. Okay, so what logistic regression does is we model the probability of an event as a function of x. And the model, I don't want you to get too bogged down in the details, but the model looks like this. So we model the log of the odds. So remember, odds are the probability of an event happening divided by the probability of the event not happening. So that would be p over 1 minus p, probability of the event happening divided by the probability of the event not happening. So we model the log odds as a linear model. Okay, it turns out that this formulation gives you a model which agrees in terms of the range of the values that can be taken on the left and the right. So the left and the right hand side are in agreement with this formulation. And what logistic regression does, just like in linear regression, is at the end of the day we get estimates of these parameters that we're interested in. So we're assuming this is the true model, and we use the data to estimate these true parameters. That's why we have beta naught hat and beta 1 hat here for simple logistic regression. Okay, so it's like linear regression in that way, except the fitting is done not with least squares, but with so-called maximum likelihood estimation. It's not important for you to understand anything about maximum likelihood estimation. What's important is that you understand that you have a model with parameters in it for logistic regression, and you get estimates of those parameters in some way based on the data. Okay? So let's look at an example of using logistic regression, and the example we're going to look at is a researcher who's interested in the relationship between age and coronary heart disease. Okay, so coronary heart disease here is a yes or no. So either an individual gets coronary heart disease or does not get coronary heart disease. And we want to know, how does age predict coronary heart disease, or how is age related to the probability of coronary heart disease? So for this study we had a random sample of 100 subjects, and a logistic regression model was fit for coronary heart disease, yes or no, as our response variable, as our y variable, and age was our predictor variable. So age was our x variable. Okay, at the end of the day, after we collected the data and ran logistic regression on this data, this is what we came up with. We got an estimate for beta 1 to be beta 1 hat of 0.157. And it turns out that for logistic regression, it's quite easy to turn these estimates into so-called odds ratios just by doing exponentiation. Okay, so if you have a regression parameter in a logistic regression, then it's quite easy to turn that value into an odds ratio by simple exponentiation. So if we exponentiate this beta 1 hat, we get an estimated odds ratio of 1.17 and a corresponding 95% confidence interval. So you immediately see that 1, remember, for odds ratios and risk ratios, 1 is the null value. So a value of 1 indicates that there are no differences. So we see that 1 is not contained in this confidence interval. So 1 is not in this confidence interval. All right. So there is a significant positive relationship between age and coronary heart disease. So we can base that on the fact that our null value is not in this confidence interval, or we could actually have reported a p-value just as well, but our p-value would have also been less than 0.05 because of this fact that we didn't observe 1 in this confidence interval. Okay, so but what does the graph, if we actually graphed this estimated model, what would it look like? So we have age down here on the bottom of the graph. This is our predictor. So age ranging from 20 all the way to 70. And what we have here on the y-axis is the probability of coronary heart disease. So if we graph this logistic model that we estimated from the data, then this is what we wind up with, an S-shaped curve. So logistic regression gives you a curve that looks S-shaped because it's constrained to be between 0 and 1, as it should be, as probabilities should be. Probabilities are values between 0 and 1, so we would expect that if this model makes sense, and this y-axis is our probability of an event, that it should be between 0 and 1, and indeed it is. So as we increase age, you see there's an increasing chance of coronary heart disease. And each year increase in age is associated with a 17% increase in the odds of CHD. We got that from this number. Okay? So that's how you interpret the outcome from logistic regression. So in this lecture we described the statistical test for continuous X variables, and we looked at a case where we had continuous Y variable and a discrete Y variable. In the next set of lectures, we're going to discuss important aspects in applied biostatistics, for instance, how to calculate sample size, randomization, and controlling for multiple testing. Thank you.